continue a discussion on oxygen transport and cost of running or endurance activities. Let's move on to running economy. So now this is going to deal with sub-maximal speeds and how economical you are at that speed, or how less or more does it cost you energy-wise to run at that speed. So just remember, for a little quick review, that oxygen consumption is defined as the amount of inspired oxygen or the volume of inspired oxygen minus the volume of expired oxygen. VO2 max is seen as the measure of the aerobic capacity, and it is the maximal volume the body can shuttle and use oxygen during dynamic activity, and this incorporates the large muscle groups, so that's a very important concept. Is the large muscle groups are very active during your max VO2 concept. It is comprised of the cardiac output and your arterial venous oxygen difference. And just for the review, remember that training effects are mostly attributed to the cardiac output via the stroke volume, right? So there's increased end diastolic volume, which is also known as the preload. The increased contractility of the ventricle allows for more forceful contractions of the blood throughout the system, and then there's a decrease in that total peripheral resistance, or the afterload. So this is less resistance to the contraction and the blood flow exiting the ventricle. We want to get into a little bit of the Tim Noakes statements, right? So this is a little bit of what he believes, and he argues that it is not the max oxygen consumption or the aerobic capacity that determines the performance, but rather the highest work rate achieved. Noakes associates peak work rate achieved with the ability of an athlete to achieve max performance during a VO2 max test. Runners that are less economical, they may reach their max work rate sooner, which limits their max oxygen consumption. So people with a less VO2, or people who are able to achieve their max VO2, may just not be able to work because they may not achieve the work rate needed to assume that or achieve that. Therefore, Noakes claims that it is the max work rate achieved during the test that is better predictor of performance. So this is important because all tests are conducted in different manners, which running speed in the work rate of importance, right? So whether we're talking about running speed, whether it's cycling, the rowing, so it's that max work rate, highest effort given. In a rower, it could be the speed or the resistance achieved. Same with cycling, it's a combination of the resistance and the ability to maintain that speed or that power. And so these are more of a better predictor, according to Noakes, than the actual value of your VO2 max. So we're going to think about this. It's a very famous analogy to deal with cars and gasoline, right? So a car may have the highest power capabilities and the biggest capacity, but the car that is the most efficient will allow the greatest travel with the least amount of gas, and therefore the least cost. So we call some cars, let's say the Audi A3 is more economical than the Chevy Corvette, but the Corvette is much more powerful. Look at that, 475 miles total range versus the 296. Very impressive. But this is a very common graph, and this is from Noakes' book. But the graph represents three runners. So you have runner A, runner B, and runner C. And if you can see, runner A has the highest VO2 max. B and C have the same VO2 max, but it's achieved at two different running speeds. So if you follow along this line, you can see the different things. There's a difference in their cost of running at the same submaximal speed, and that is dealing with that 18, 19, where you can see running economy there. In this case, the person with the highest capacity has the least economical, was the least economical at the submaximal speed. So that means that, yeah, they had the highest power, VO2 max, and it's achieved at the medium speed, but it's not. They also had the most cost at that submaximal speed. So if they all ran the race at 18.2 kilometers, we'll say, per hour, it would cost runner A more. So therefore, they would tire and fatigue earlier, or become more susceptible to hitting the wall earlier than the other two. So this becomes greatly important during endurance runs, whether you're talking about running or cycling or triathlons. Because the concept of performance is the runner can achieve a higher running velocity workload, should therefore be able to maintain a higher running velocity at lower cost. However, this concept does not hold true for all. Many new age athletes are training at a higher percentage of their aerobic capacity, and this is where you have the incidents like here, where um, runner C may have the lowest VO2 max, but he actually achieved the highest speed at that VO2 max. Um, and he probably was therefore able to train at a higher speed during, so that 18 is a relative low intensity for him. Therefore, it's more economical for him than the other two. So now I want to backtrack a little bit and define what economy is. I put running economy, and a lot of my examples will be related to running economy, but I want to make sure that we all know that this could very well transfer to swimming, to cycling, to rowing, to any form of submaximal aerobic exercise, right? So the definition of an economical person or running economy is oxygen consumption at a submaximal workload. Now, what that means is somebody who uses less oxygen at a given workload is considered more economical than somebody who uses more oxygen at that same workload, right? So this is where you less and more, right? So this is the idea that for VO2 max, the person that uses the most oxygen and has the biggest capacity is the captain, is the king. Well, here the person has a less value, the less oxygen consumption at that given workload is considered the more economical runner. Therefore, they are the king and they are better. The units are the same, liters per minute, or if you normalize the body weight, it's milliliters per kilogram per minute. And then what we do is we define this by a steady state. Now, a steady state is basically unchanging of that internal environment. So there's a few criterias, and it's after a couple of minutes of exercising, then your body can adapt and warm up, right? So truly this is kind of that warm-up period where your body continues to climb. Then you get to that area where your body feels warm, normal, so it's an unchanging of that internal environment. We measure this by a heart rate, steady state heart rate. The RER is steady. And then there's also a VO2, the cost of, or the volume of expired and utilized O2 is steady. It's usually between 100 milliliters is what they classify as that steady state for VO2. I typically use the VO2 as my measure because, again, you know my feelings in heart rate, but RER as well I can use to determine between one speed and the next two submaximal workloads, which one is a better fit for that individual, right? So they are costing them more to work at that workload and cost of oxygen at said workload versus another. But all three of these are used as an unchanging internal environment as you see that plateau effect in steady state. So this is actually from the article, one of the articles that I posted. It's actually a summary. And this is a description of effects or different things that have an effect on economy and running economy. Again, this is strictly going to be towards running economy, but it can transfer out in different areas and different magnitudes from different concepts to other endurance economies like cycling and swimming and rowing. Just a little bit of the ideas will be a little bit different and drawn more towards those particular things. But you see training, the environment, the physiology of the individual, the biomechanics of their movement, and their anthropometry all play and take a role into deciding some of these economic. So now I want to break it up in that little diagram into the individual components. We're going to start with anthropometry. And there's an inverse relationship between the body mass and submaximal cost of locomotion or running. And it's heavy people utilize less oxygen. So the heavier you are, you utilize less oxygen. Typically this kind of goes into play with your heavy people are generally less aerobically trained. And that is truly kind of where this is. Even if you have a very high muscle concentration and muscle mass, you tend to lose more oxygen because typically those people are more anaerobically trained. There's a limb length and mass distribution. Those are unknown on their effect to running economy. And there's a few reasons why that. Limb length, we can simply change the way we move our patterns to make it more economical and change the moment arms and the lever arms and have a good way at that. There is no gender effect. The gender effect is usually related to the mass sizes, so that goes back up to the mass. But if you match for body type, there's no gender effect. Africans and Asians use 17% less oxygen than their Caucasian counterparts. um, lying down, sitting, and standing. But this activity, this relationship during activity is unknown. So there's still some need to do some further investigations and whether they're just the metabolic and normal basal metabolic rates of oxygen consumption, or if this transfers over to activity. So this would be interesting to see. And this could explain why some of the Kenyans and Ethiopians are better endurance runners than, or are leading the endurance charge for running at this point. So now we'll get to something that's really dear to me. You know, I'm a biomechanist at heart, so biomechanics is an area that I think is very important in the economy. Um, One of the biggest ones is this vertical oscillation. So that's the up and down motion of the center of mass. It's considered to be more economical if you do a gliding motion, so less of that vertical oscillation. So what that means is most of your energy is being transferred into the forward propulsion or the forward momentum, keeping your horizontal velocity constant. By moving up and down, I'm wasting energy, propelling me up and down. Therefore, I'm costing energy to decelerate my downward motion and turn it back upwards. This also increases some other aspects of the biomechanics of running. Before the economics, we're going to talk about vertical oscillation as being gliding more economical. The mass spring model, or the stiffness of the lower extremity. So as you increase stiffness, and what I mean by stiffness, so as I strike the ground, the angle at which my ankle, knee, and hip stand, if they change a lot during the stance phase, then I'm less stiff, I'm more compliant. If they do not change much during ground contact, then I'm considered to be a stiffer runner or stiffer contact. So increased stiffness increases the economy. That means you're using more of that stretch shortening cycle, so you're not having to spend a lot of oxygen consumption to decrease that downward motion. Increase knee flexion, so therefore you are becoming more compliant. You reduce economy, so you use more oxygen during the concept. If you want to find some funny things, go ahead and do a Groucho Marx search. And so there's a concept of Groucho Marx running and walking that by an exaggerated knee flexion, you can decrease the impacts, but you increase your oxygen consumption. So it's confusing on whether it's beneficial or not. So the conversion of muscle force and storage. So an eccentric is the loading mechanical energy stored. Concentric is more of your recovery. So it's that conversion of, as I strike the ground, eccentric to concentric contractions, and how those affect running economy as well. That has to deal with more your plyometric training and the stretch shortening cycles. And as you can utilize that more to your benefit, you will utilize less oxygen to cause the muscle contraction. It is theorized that we all have a preferred stride frequency and stride length that yield optimal costs. Oftentimes you'll see in some research studies that as we shift one person plus and minus, they may become more optimal. So it's not necessarily that we all choose the most economic, but we all have a preferred more economic path. Cyclists have a greater percentage of type 1 fibers. Now this is again according to the paper, and for those of you that were in the previous lecture last week, understand that some people theorize that there's not these difference in type 1 and type 2 fibers, but there's a general consensus at this point that there are the difference, but we'll see how that goes in about 5-10 years from now, see if it shifts. So now let's get into physiology and truly what this class is about. But children have a higher consumption of oxygen. They're truly more or less efficient beings because they're still trying to utilize what they need to do. Speeds change gait parameters, which directly alter triathlon data. So that's the kind of concept of stride length and stride frequency. We'll go to the very bottom of this graph, the influence of different running speeds. As speeds change, all kinematics change. Therefore, everything related to the cost of locomotion is going to be affected. This is truly difficult to measure in the real world. And that's why so much of this is measured in the laboratory. But speeds affect everything. The faster you run, typically the more oxygen is consumed. The slower you run, or the slower you move, the less oxygen is is consumed. Now, this goes into the play of somebody who's used to working at a certain work rate may be more economical. Increased ventilation has a positive correlation with decreased running economy. So the more rapidly you're breathing, you decrease the running economy. So you utilize more oxygen to do it, right? So as I'm ventilating faster, I can't talk anymore. I'm becoming less efficient at utilizing the oxygen that comes in. Therefore, it's costing me more to move. Higher core temperatures increase the volume of oxygen at a given speed. Therefore, you're less economical. And then the increases in metabolic cost from a reduced running economy increase maximal VO2. This is through augmented circulation, ventilation, and sweating. So now we're going to start talking about something that I hope to get into better and more involved with later on in this class, and that's training. There are many forms of training, and this will talk about plyometrics, resistance, some of the training stuff, and then your traditional kind of speed volume intervals. But interval and strength training have been shown to increase your running economy. And so what that means is you are able to work at the same workload with a less oxygen consumption, right? So when I increase your running economy, I'm decreasing your cost of oxygen. This is seen through shorter contact times and the ability to have faster forces. Plyometrics, and this is through that stretch shortening cycle. So it strengthens eccentric and connective structures involved. So go back to that stiffness concept. This creates a stiffer model of the tendons and ligaments, with therefore you can utilize that turnover from eccentric and connective tissues structures to produce and generate more power in the stretch shortening cycle. The current training so this is doing strength and endurance training at the same time, has been shown to improve running economy, but not your VO2 max. So this is an area that I hope somebody in the class takes on as their project, because this is an area, it's really important how you do the combination of your strength and endurance training on whether you see the most improvements. And we'll talk about this later on in class and truly the training and resistance portion of it. But it's very important how you concoct this concurrent training and what type of strength or resistance training you incorporate. Again, we talked about this last time. So the effect on elites, though, for these training and for some of the other avenues of plyometric resistance is unknown, right? Because now you're dealing with elites that are already greater than 70 mils, and we saw that upwards of 97 the other day in class. But the effect on this class of individual is still quite unknown. Whether it can improve your VO2 max or solely how it can improve their running economy. Most of the studies have been done general. So also VO2 max remains stable. A little change with intense training. Now this is dealing with that elite population because what we have seen in the last lecture is your VO2 max can be quite increased with training. But training effects increase your running speed at lactate turn point. Now, the lactate turn point is is basically, some people call it a lactate threshold. It's that point where now you all of a sudden start seeing the accumulation of lactate. So you're trying to get towards that anaerobic, more metabolism and leaving the aerobic. So you're pushing back, or you're creating the ability to run faster for a longer period of time during your training effects. So this needs to be done gradual and progressive to increase your running economy. And that's what you'll hear a lot of people talk about, lactate threshold training. And this is what they're talking about. They're trying to turn and push back that turn point closer to their VO2 max. Because if you can do that, you can work at a higher workload of your VO2 max, which is going to make you much, much faster. For every 5% increase in your running economy, they've estimated to be about 3.8% distance improvement, which is a big difference if you're so close to qualifying for Boston or the Ironman Kona. This can make all the difference in the world by increasing your running economy, or that running speed at which that lactate turn point is achieved. So let's go further and talk about the environmental factors, which is the last portion of that diagram. But environmental factors have a huge effect on performance and how people can maintain homeostasis throughout their body.
And we'll spend most time at altitude, but I want to be clear that we're going to spend a lot more time on altitude and heat later on in class, so I'm not going to spend too much here. But know that altitude exposure through is thought to improve running economy, but this is still for debate, you know, and what you'll see with these next two is that majority of the research is done on highly trained runners. So I caution a lot of people in the average Joe on whether they need to do altitude training. This is not saying that you don't have to acclimatize to the altitude at which you're going to perform your activity. These are completely different concepts, right? So there's a 1% increase that they've seen in elite triathletes that slept suit versus those that didn't, and again, specifically with cycling. Three other studies did this normobaric hypoxia. So that's training in the altitude chamber. So not actually going to altitude and returning back down where the pressure gradients are different, but going into a kind of an environment that is non-normal with a reduced oxygen concentration. So whether the reduced oxygen concentration and the pressure gradient have the same effect are unknown, but the hypoxia training inside the environment has seen about a 2.6 to 3.3% change in highly trained runners. Again, elite, highly trained, and what that has to differ. But there are some proposed mechanisms behind why this is, and it's the decreased cost of ventilation. There's a shift upwards to more of a glycolytic form of AT generation. There's an increased carbohydrate utilization. Then there's an increased ability of the excitation contraction processes that contribute. Now, the overall concept with heat is going to be mostly to that core temperature increase and all the detrimental effects of that. We'll get more into that later because I want to talk not just about heat, but also about the cold and more of the humid as well. So we'll get to that conversation in a later date. But understand that the main concept with heat is through the core temperature concept and maintenance of stroke volume and how that happens. But one of the other factors I want to talk about is the mass and what we wear on our feet. And this is through a concept of it costs you more to bring that swing leg through because you add weight to it. And so it's been shown to have about a 1% increase for every 100 grams added to the foot. And so that's, do you add the weight distally, more distal, more proximal? But these are some spring roots, right? So the concept that we talked about earlier is if you can return through that stretch shortening cycle some of the energy that's stored, and that's what this is theorized between these spring boots, where you're utilizing that spring load. But the problem with these are they're just way too heavy, so it hasn't produced what they wanted. All right, so going forward, I want to use this kind of Fletcher et al. Study to kind of illustrate a few things about running economy, VO2 max, and this lactate threshold period. But we're going to focus on subjects 1 through 3. Their VO2 maxes aren't quite different. There's about 2 ml per kg per minute that separate them two. But we'll talk about 1 and 3 for a second. Following the VO2 max column, you have a speed at lactate threshold. So the mechanism at which they conducted their experiment was they kept increasing the speed at a level surface on the treadmill. And they kept taking blood measurements to identify the lactate threshold. So when they had a huge burst in the amount of lactate in the blood that they took. And what they did is they backtracked on the previous speed is what they measured. So at this point, they had the speed at which there was an increase, drastic increase in blood lactate. And so that was the speed of lactate threshold. And what they did then is they identified the cost of running at that speed, and that's what that percentage VO2 max is. Because following that, they put the treadmill back to the previous speed, and at that point, now they increased the elevation of the treadmill to finish the VO2 max test to identify that VO2 max you see there. So now you have 2 runners, 1 and 3, difference of 0.3 mLs, so essentially the same VO2 max. But their speeds of lactate threshold are quite different. One has a 317 meters per minute, and the other one is 292 meters per minute, which is quite substantial. It's more than, it's about 25 meters per minute difference. And you also see that the cost of it for subject 1, who was a faster one, was at a lower percentage of his VO2 max. So he was costing him less to achieve that
speed. So he might be trained better at that lactate threshold. And that's what I take from that. So then if we look over more at the um, cost at the very end, and we're going to focus on the middle column. We'll focus on the 85%, just because I want to illustrate with one. So what that means is 85% is they conducted a 5-minute submaximal test at 85% of that speed of lactate. So they multiplied 317 by 0.85, and so it's about a 269 meter per minute speed for subject 1. For subject 3, it's about 248 meters per minute speed. So there's a difference in 20 meters per minute. 1 is running faster than 3, but it costs 1 more to run at that speed, which is faster. Cost him less to run at that speed, which is faster than 3, which is a slower speed, but it cost him more, right? So the caloric unit per cost, and they're burning more calories at that speed for C3. So this kind of shows you the idea of lactate threshold training more economical at a particular speed or distance. So this is a relative concept of VO2 max or running economy, right? So this is not running at the same speed. They're running at a relative intensity as it relates to their speed at lactate threshold and VO2 max. So this is how we can compare kind of apples and oranges with speed, as we use a relative intensity and say one person is more economical at 85% of their speed at lactate threshold than the other is. And then the graph over there kind of shows you on the two y-axes. On the left-hand side, you have the cost of locomotion with the oxygen consumption. On the right hand, you have the caloric unit cost. And then now at the bottom, you have the percentage of their speed at lactate, right? And you'll see the oxygen consumption. The top graph represents the oxygen cost, and the bottom is caloric. You see caloric cost is pretty much a linear trend. But you can see that the oxygen consumption, we call that kind of a U-shape. So that's the beginning of the U-shape, and it seems like 85% there is the bottom or the apex of the U-shape, which means that is the speed at which people feel most comfortable or are more trained at to run. If you go anything lower that speed, you may be spending more energy during the bouncing or the vertical oscillation, so you're decreasing your efficiency at that speed. Where the same is at a higher intensity, you're less efficient. This is another graph from that same study, and this shows each colored line here is each individual subject at its 3 absolute speeds, and it's interesting to see that as people tend to run faster, there's actually a decrease in caloric cost. So this is more trained in highly more elite or non-recreational runners that run faster tend to be more economic, and this can be for that training status. And typically those people do more of that lactate training threshold where they're doing fartlek runs or some kind of interval runs that push back that lactate threshold. This is another biomechanical graph, and this has anybody that's seen GRFs or ground reaction forces during running. This is very typical. Left-hand side, the vertical ground reaction force. You have a number of them from what you consider kind of to be a forefoot to rear foot striking. But the one that we're going to focus on is the one in the middle, the horizontal force. And what this illustrates is the idea that the more contact time or depending on where you strike the ground, you could have an increase in your braking phase, which is that portion going down, the first part of that graph, where it's below the horizontal axis, which will require you to have a greater propulsive force to propel you forward. So a more economical runner is going to have less of that braking impulse, which is going to require them or demand less of a propulsive impulse to keep that horizontal velocity going. So the goal of running is to maintain a horizontal velocity. So the less you can have fluctuations in that, the better and more efficient you are to maintain that horizontal velocity. So by reducing your braking impulse, you can reduce your propulsive impulse. So then the final one I want to talk about is I want to revisit a little bit of that vertical oscillation, center of mass displacement, and mass spring model concept. So here we have vertical displacement or vertical oscillation is the highest points of your center of mass during the locomotion minus the lowest point. So this incorporates the aerial phase, and then it incorporates, and typically you're at the lowest during some sort of mid-stance, plus and minus where mid-stance occurs. But that's where you're at your lowest. So it's that difference between the highest point and the lowest point. And those people that glide have less of this vertical bounce or less up and down movement of the center of mass. Therefore, they're able to maintain more of the propulsive force that's going forward as opposed to up. And then you have the mass spring model. And this is ideally representing the lower extremity as a spring. So going back to that stretch shortening cycle where you're being able to load the spring and recoil, which aids in your propulsive. The more effective you are in loading and recoiling, then you are a more efficient or more economical runner. So this is where that comes into play, where you're increasing your stiffness or becoming more compliant. More compliant runners cannot store and return energy as well as a stiffer runner. And sorry, I guess that wasn't the last one. This is the last one, and this is going back more to that concept of we all have a preferred stride frequency or stride length during running, and this is that U shape again. So stride frequency up on top. You'll see 3 different speeds of running and how you have your preferred stride frequency at 100, and then as you get faster, that preferred stride frequency tends to shift a little bit towards the right in the middle there, and that's the U. And then you have your preferred stride frequency. Stride length, and it's there. And as you decrease your stride length or you increase your stride length at a particular speed, there you have what happens with your U shape, and the stride length is determined upon your speed and your stride frequency. But if you change either one of them, either way of that optimal, then you will cost you more oxygen to produce, so you become less economical. So there is that bottom of the U for both stride frequency and stride length according to every speed that you run at. That will be optimal, and that's an interesting, important to find. So that concludes our talk about submaximal running and our submaximal workloads and running economy. So look forward to having your quiz and have some good debate. Please come ready to debate.